Hello, Alex Osels here from Boston University. So if you're an EK307, you might have built this circuit last week. So this is our heartbeat detector circuit. We use a loudspeaker as a transducer, and if you put the loudspeaker on one of your arteries, when your heart beats, you get a pulse, it moves the loudspeaker, a little bit of current flows, so you develop a voltage across the speaker terminals, gets amplified, filtered, amplified, and filtered, and it appears on the output over there. So we're going to break down the circuit a little bit today, try to mathematically analyze it. So the idea here is to really summarize what you learned in EK307 and try to apply it to a real life circuit. So you might look at it at first, it's kind of daunting. There are a lot of things in there, the 3 op amps, a bunch of resistors, a few capacitors. So how can we simplify this down? So the first thing I could see that I could simplify is this circuit right here. So if we look at this amplifier, so it's a voltage follower, it has a gain of 1. And the input is coming from a voltage divider, so R5 and R6. And in our circuit, they're the same value. Maybe I use 10 kilo ohms for those. The exact number is not too critical as long as they're not drawing too much current and just wasting power. So the main thing there is we want to split the 5 volts in half. So we get 2.5 volts there. And because this circuit has a gain of 1, we know we're going to get 2.5 volts on the output. And looking at some of the other parts in here, knowing that these values are in the tens to hundreds of kilo ohms, I could make a good assumption that the output of this op amp has a very small resistance. In other words, it looks like a strong Thevenin source. So I could take that out and replace it just with a 2.5 volt source. So before I erase it though, and look, there's another capacitor over here, C1. And C1's connected between the 5 volt supply and the ground. And you're saying, well, what is that doing? Well, that 5 volts is connected. You can imagine there are actually lines connecting all these op amp power supplies together. And the C1 is what they call a bypass capacitor or a decoupling capacitor. And what that does is it functions to lower the impedance of the power supply. So say if your actual 5 volt power supply going into your circuit, if we made a Thevenin out of it, you had a resistance that was slightly higher than you wanted. You know, this R was a little bit too big. And therefore, when the op amps took a large signal in and amplified it, it was drawing a little bit too much current, and the voltage here was dropping below 5 volts. If you put a capacitor across here, and this capacitor represents C1 over there, it'll act to lower the impedance of this input to the circuit right there. So that's a common thing to do. A lot of times you'll put a 0.1 microfarad capacitor across the input or the power pins on op amps. It's just a standard thing. So that's why we have it there. But if we're assuming ideal circuits, we could take that out also and just say it's a given we have good power supplies. So now we could erase all this stuff. That's getting simpler already right there. And we know that we really can just say that this is a 2.5 volt voltage source. And I'm going to move it up here a little bit just to make some more room later on. And it's a DC source. It goes to ground. So what is that source doing anyway now that we turned it into just a symbol? And so it's 2.5 volts. So it's connected to the ground or the reference terminal of the op amp inputs. So those are the references over there. And what we're doing is we want to offset the zero signal. In other words, when there's no signal coming into the op amp, the signal on the output, we want to reference that to 2.5 volts. So instead of having these terminals typically tied to ground like we do, we are bumping them up to 2.5 volts. And when we do that, that allows the voltage at node A to swing positive relative to the 2.5 and negative. Because you can see our power supply for the op amps is 5 volts to ground. So that means that our output could swing from 5 volts to ground. So if we say that the zero signal input or output is 2.5 volts, then we can go above 2.5 and below, and we can get a biphasic signal. And that's important because our loudspeaker moves in both directions. So that means that current flows in both directions, so we could develop a positive and negative voltage across there. And we want to be able to see that. Like if we have a small wiggle there, we want to see a larger wiggle here, where the bottom of the waveforms are not cut off because we're initially sitting at 0. So that's what the rail splitter does. Now it's a symbol. The other thing that we could simplify is the loudspeaker. So the loudspeaker actually has a really low resistance Thevenin circuit. It's got a coil in there. And so we could simplify that down to be a voltage source. And we're going to call it a sine source here because that's how we're going to do our analysis. So it's a sinusoidal source, and it's somewhat variable. So the frequency of that and the voltage can vary, and that's going to be connected to a function generator for our measurement and analysis. Now we could look at this circuit right here. We have an op amp. This is a non-inverting op amp, so things are looking a little bit simpler now. So in my particular circuit, I had 6.8 kilo ohms for R1 and 100 kilo ohms for R2. So if we do the gain equation for that, we know that V out over V in is going to be 1 plus R2 over R1. And then let's see, so we have about 100. So it's probably about like 14-ish, 100 divided by 6.8. So 14 plus 1 is 15. So that's saying that this circuit right here has a gain of 15. And so there's not too much interesting other than that gain of 15 here, and the fact that then it's an important fact that the output here can't go above 5 or below ground. So that's something we'd have to consider. In other words, like if we had a 1 volt sine wave on here, and then we multiplied it by a gain of 15, we're going to be going, plus 15 and minus 15 if that was amplitude, and that's clearly not going to work. It's going to clip the signal. So that means that we have to mind what the input voltage is here, and so we need to keep it small so that this large gain doesn't cause the clipping on the output. But for simplification's sake, we could take that and turn it into a black box. Take all that out of there, straighten this wire out. Sometimes it's nice to make it neater. And then, so we just have a black box right here that has a gain of 15 in it. And I'm going to make this connection over here, really just to mention that it's referenced to 2.5 volts. So for the AC analysis, that won't matter very much. Then this connects over to here. So we just simplified the front of our circuit down quite a bit. So what do we have left? We have 2 capacitors, 2 resistors, and an op amp. And when I look at this, if you take a step back and look at it a little bit, so you might see a familiar pattern. So if we group C2 and R3, and we called those Z1, so it's complex impedance 1, and we group C3 and R4, and say that's complex impedance C2. So thinking back to just regular old op amp theory, if we think of or inverting op amps, if we have, this is R2 and R1 over here. So we know the gain of this circuit, and that goes to ground. The V out over Vn is going to be minus R2 over R1. So that could generalize where these don't have to be real resistances. They could be complex, so they could be Z1 and Z2. Therefore, this equation right here would satisfy that. So we have Z2 and Z1 in there. So output over input equals minus Z2 over Z1. And we just boxed our elements. So now, can we simplify these down, right? So we have a capacitor in parallel with a resistor over here, capacitor in series with a resistor over here. So if we look at this this combination right here, what we call Z2 first, how can we simplify that? And so we could come over here. We know that when we have devices in parallel, the equation looks like this reciprocal equation where you have 1 divided by the reciprocal of one of the impedances plus 1 divided by the reciprocal of the other impedance. So the impedance of R4 is just the real value of R4, so we put that over here. And then we know that the impedance of a capacitor, in this case, it's 1 over j omega C3. So we get the reciprocal of that, so that would end up in the numerator over here, j omega C3. So this is our equivalent impedance. So we could make it a little bit simplified by multiplying everything by R4. So that turns into a 1 over there. So now we have this equation, R4 divided by 1 plus j omega C3R4 equals our Z2 impedance. Now we could look at the Z1 impedance right here. So we have C2 in parallel, or C2 in series with R3. So those sum together. So we have R3 plus 1 over j omega C2. And we might want to give these a common denominator just to make the math a little bit easier. And so if we put that j omega C2 over there, then we could simplify that out and say that we have 1 plus j omega C2 R3 over j omega c2 equals z1. So now we have our two impedances. That's the 2 right there. And we could put it back into that equation that I erased, which was just minus z2 over z1 equals our transfer function. In this case, maybe we'll call it h as a function of omega, because omega is a thing that changes, and here omega is angular frequency. So let's do that here. So we have R4 divided by 1 plus j omega c3 R4. And we take this and flip it over, right, because we're dividing by that whole entire fraction. So we're going to get the j omega c2, and just to make it a little bit simpler, I write it in front of here, j omega c2, and then we're going to multiply the denominator by that numerator, 1 plus j omega c2 R3. Straighten that out there. Can't forget the negative sign. So that is our transfer function, and that's a function of omega. I cleaned up the whiteboard a bit, and now we have our transfer functions over here. So once again, this equation right here is describing this, we call this our V in 2, and then our V out right there. It's a transfer function that is V out over V in 2, and so we have, it's a function of omega of angular frequency. So this is what we have right here. So what does this mean to us? And the the way to look at this, kind of quickly without getting too much into the math and doing all the formalities of everything, would be, say, if we looked at the h of omega on our vertical scale and our j omega on our horizontal scale, and if we look at the limits here, like as this goes to, as omega, or as j omega goes to 0, which is really as omega goes to 0, because j is an imaginary number, what's going to happen right here? So we could see that, as omega goes to 0, these two parts of these polynomials right here are going to go away. They're basically going to vanish, or we'll be left with 1 times 1, so our denominator is never going to go below 1. But the numerator can keep on getting smaller and smaller, so there's nothing preventing that. So if we could imagine at 0, our gain would basically be 0. In other words, the voltage on our output relative to our input would be 0. Nothing would get through. Then as we start to move to higher frequencies, this is going to increase, and these two are going to start to increase. But for very low frequencies, like if the j omega c3 R4, or really omega c3 R4 is still much less than 1, then like this is not really having a major contribution here, so the denominator is still going to be 1, and this is going to be increasing. So one thing to note here is we're really not considering the negative sign. This negative sign came from the amplifier right here. So for now, we're going to pretend it's not there. We're just going to wipe that out because we're looking at sine waves. So as frequency is increasing, we're still much, omega c3 R4 and omega c2 R3 are still much less than 1. So the ones are dominating down here. So, and this kind of looks like the slope of a line, to an approximation. Frequency's going up. This term's still dominating, so this is kind of marching up as a slope that's related to that. And at a certain omega, or a certain j omega, these two, or one of these, is going to start to be significant. So say that j omega c2 R3, or omega c2 R3, is larger, it's greater than the omega c3 R4. So that means that, as the omega is increasing, this component right here is going to start to become significant relative to the 1 over there. And when that happens, because it's in the denominator, right, our slope, we're not going to be going up at that nice slope from the numerator. We're going to start to lose slope as this gets larger and larger. And then, as things start to get really large, it's going to dominate to the point where the 1 is almost insignificant. And now we just have j omega c2 R4, battling out with j omega c2 R3, and it's going to end up being a straight line for a while. Now, say we're getting to the point where the omega c3 and R4 is starting to get significant compared to this one over here, and now both of these terms in the denominator are going to be fighting the numerator term right there, and the magnitude is going to start to go back down again. So if you look at this, if we imagine this was some frequency scale. Right now it's angular frequency down there, but it could be hertz. We're not too concerned about the absolute of this. We're really just looking at the picture. Like, what is this shape right here? This is a magnitude type of response, voltage out over voltage in. And it's saying at really low frequencies, we have nothing coming out. At these middle frequencies right here, we have signal coming out. We don't really know what that level is. And then as we get higher and higher, then the signal starts to go off. And this is what they call a bandpass filter. And that's because it's passing a certain frequency band, which is what's at this high point right here. So it's passing that band. So that's just a brief look at it. This is not a formal way to do the math right here, but we're just trying to get a sense of what's going on. Like, if you had no idea what this is doing, you can look at those limits, very small omegas, and then as omegas getting larger and larger, what's it doing to this equation right here? So now let's go look at the actual circuit and see what it's doing. Okay, here we are at the lab bench. We have our heartbeat detector circuit. So we have the loudspeaker as the input. We have an oscilloscope. We're connected to the blue channel here. And if I tap on the loudspeaker, you can see that we're getting response. So the blue is the output of the second operational amplifier, the one with the more complicated transfer function. So things are working well. So we have a power supply down here. This 5-volt power supply is providing the DC to power the circuitry. And then up here we have a function generator, which is not connected yet. But what we're going to do here is we're going to take the loudspeaker and disconnect it, and we're going to plug the function generator in its place, because it's something that's deterministic and controllable. And more importantly, the function generator can generate signals that are pure sine waves. And that's really important if we want to be able to use that transfer function analysis that we just went over, because the input is omega. So if we're putting in discrete omegas or discrete frequencies, that's going to be very difficult with the loudspeaker, especially with me tapping on it. Like, you can see that's not a sine wave. So we could disconnect it from the circuit, and then we'll use our function generator as our input. So I have my function generator, and as I mentioned before, the gain of the amplification is so large, and the amplitude output of the function generators is also large, meaning that if we put this 1.3 volts in here, we'd saturate our amplifiers right out of the box. So we don't want to do that. So I made a voltage divider that has two 100Ks in series. So that's for 200K, and then there's a 2K resistor that goes to the voltage reference there. And that basically attenuates this signal by 100. So instead of getting 1.3 volts, we're getting 13 millivolts on the input to our amplifier. So we just made that connection. You can see we have a sine wave on our oscilloscope right here. So that's the sine wave that we're feeding into. It is getting amplified and filtered and is appearing. So when you're taking these kind of measurements, it's nice to look at the input of the circuit to see what you're putting into the circuit. So coming out of my function generator, I have this T over here, and then I have another BNC cable that goes to channel 1 of the oscilloscope, and I could turn it on, and now you could see we have the yellow, which is representative of our input signal, and then the blue, which is the output from the circuit. So here we have V out and V in. So now we could measure some transfer functions. And so before we do that, one thing to note is that the yellow trace voltage is not attenuated by 200, and we don't want to do that because then the oscilloscope will have a hard time picking it up. It'll be noisy. So we'd say that in our minds, we'd literally take the amplitude of that yellow signal and divide it by 200. And if we look at the actual amplitude right now, so we're on 1 volt per division. We're about 1.25 divisions. Well, that makes sense. It's actually 1.3 volts peak to peak on here. So that's our input divided by 200 will give us the voltage on the input of our amplifier. So channel 2 peak to peak is looking to be about 3.2 divisions. So that's about 3.2 volts because we're on 1 volt per division over there. So now when we did the analysis as a function of omega. We know omega is related to frequency in hertz. Omega equals 2 pi times f. And then so, omega divided by 2 pi equals hertz. So they're linear units, so now we could go over here and change the frequency. So the stimulus frequency is 600 millihertz, and that's a fairly low frequency for what we usually do in the lab. It's less than 1 hertz, meaning that the period of this is less than 1 second. And we could turn this knob right here to do what we call a frequency sweep. And first I'm going to go to lower frequencies, and we can watch what happens. So we could see the frequency changed. So it's a much lower frequency, around 100 millihertz right now, meaning that we have a period of 10 seconds. And you could see that the amplitude of the blue trace got a lot smaller. So I could change the time scale on the scope a little bit. And this is happening in real time, so we actually have to wait for the signal to go through a few cycles. And you could see, compared to before when we were at 0.6 hertz, the amplitude now is only about 1 volt per division. So where before it was about 3.2, now it's 1. So that's showing the effect of the bandpass roll-off. As we go to lower and lower frequencies, that numerator is really attenuating the signal. Basically the numerator is the zero in the equation right there. So the lower the frequency goes, the closer that's going to get to zero. So now we can go the other way, and we'll step back up in these 0.1 hertz increments, and you can see the output is getting larger in magnitude. It's growing, and we can see this in real time as I'm turning the knob right there, and it keeps on getting larger. So now we're at 1 hertz, and look, it's starting to get smaller. So the amplitude is slowly starting to get smaller there. And you can see that. I could go even faster to make it more dramatic. And so now we're at 3 hertz, getting smaller yet. And then I could change the scale on here. And we're on this, what we call a roll waveform, so I'll stop it because we're not fast enough to actually trigger a sweep on the screen. And sure enough, as we go to higher frequencies, the output is also attenuating versus the input. So in addition to the magnitude changing as we change the frequency, you might notice that the phase of the sine waves is changing. So the phase of one relative to the other one is really the time delay. And if we're thinking in degrees, 360 degrees of phase delay would be when we move from one peak to the other one. And so 180 degrees of phase would be when we move from a peak to a trough, or from a zero to the next zero, those kinds of things. So looking at this waveform right here, we could say that it appears that the blue waveform might be leading the yellow waveform in time, or it could be that the blue waveform is lagging the yellow waveform by this amount of time. And because it's a sine wave, it's hard to tell. I mean, that's one of the natures of sine waves and things like the unit circle and these cyclical waveforms, is that you can wrap. And the actual determination of whether it should be a phase lead or a phase lag is going to be something we'd have to look at the Bode plot to examine. But now if we turn back on the sweep right here so that we're running again, and let's see if we can move to a slower scale. There. So now as I go back down in frequency, does the phase delay change? I went a little too far down there. And so if we look at this frequency right here, so this is different. Now it appears that the waveforms are almost 180 degrees out of phase. So we have a peak and a trough, and they're alternate polarities right there. So if you recall, the output amplifier, right, the one that had the capacitors in the feedback and on the input, was an inverting amplifier. So considering that's an inverting amplifier, that's multiplying the wave by -1. So it could be in this situation right here, around 700 millihertz, the only phase contribution we're seeing is literally the negation of the signal. So the output signal is negated relative to the input signal, and that's what we're seeing right here. And coincidentally, it's coinciding with the point where the magnitude is the largest. So you can see as I go to lower frequencies, as the magnitude gets lower, our phase shift is going to be different. Compared to when it was at 0.7 hertz. And then as we go up in frequency, so this is kind of fun, we could see the effects in real time as we go up the frequency. Right there. You could see the phase is changing from one waveform to the other. So in addition to that magnitude change, we also have the phase change. And one thing that's also might be obvious, as I change this frequency really quickly, we get non-sinusoidal signals. Like if we look at this signal right over here, like this is a non-sinusoidal transition. Like we went abruptly from this very low frequency sine wave to one that was about 10 times larger, and then over here again. when we have these non-sinusoidal transitions, it's important to know that you'd have to include the frequency content of the non-sinusoidal transition. Like that isn't a single discrete frequency. So in order for this frequency domain Bode plot environment to work, you'd have to account for all the frequencies that are occurring at that transition. And you could use superposition to do that. So here we are with a screenshot of the schematic with the transfer function in it, and then a Matlab script that I wrote, which is going to model what's going on in the circuit. So one thing to note, that the first line right here is that input attenuator. I mentioned that earlier in the in one of the oscilloscope labs or videos, where I put in a voltage divider. So two resistors, there is a 200K and then a 2K resistor there, and that acted as a voltage divider to lower the voltage going into this input stage, because the function generator minimum output was 1.3 volts, just because the way it was set up. I had to divide that by 100 in order to make the signal small enough so we wouldn't saturate the gain stages. So that has been done, and that's captured in this line of code right here, where I have an input attenuation. And then I have my function generator voltage peak to peak input, and that's appearing right here on this sine wave source, which is a function generator. It's something where we could change the frequency, but the voltage is fixed. Then I put in my values for my parts. So R1 and R2 are the resistors that set this gain to 15. R3 and R4 are over here. Those set the gain of the inverting stage, which is also a bandpass filter. Then we have C2, which is 100 microfarads, C3, which is 1 microfarad. So we learned that C2 and R3 are really responsible for the high pass filter effect. Like those make the zero and the pole. So, and then the C3 and the R4 are responsible for the low pass effect, which is primarily the effect of this pole over here. So we have our voltage reference in here, which I actually didn't use. Then I made a frequency vector, which is a log space number going from 0.001 hertz to 1000 hertz, and there's 100 points in there. And then, because I think more in frequency in hertz, I made a conversion. So the great thing about computers, where I could convert the frequency into omega, which is the angular frequency that we're using in the equations. So next thing I did was I took the complicated, well, maybe it's complicated transfer function of the second stage right here, and I broke it down into the polynomials. So we have the numerator, which is a 0, and so that's going to be 1i, which is really j times omega times c2 times r4. So that's my 0. I call it hz. And then I have one pole for my low pass filter. So that's this pole right here. So 1 plus 1i, which is j omega c3 times r4. Then the second pole, which is our high pass filter pole, is 1 plus 1i omega c2 times r3. And then for the Bode plot and for frequency response in general, we want to look at magnitude and also phase. And so we know that when we're doing the math on the board over here, if we get the magnitude of the 0, and we divide it by the magnitude of the poles, that'll give us the magnitude for the transfer function. And that's what we have right here. This abs function is the Matlab magnitude function. In other words, if you have a vector, then the absolute value finds the length of the vector. So to find the magnitude, we take the absolute value of the 0, and then we divide it by the absolute value of each of the poles, multiply it together. And you'll notice we use this dot divide over here. And in Matlab, the dot says that we want to do it on a point-by-point basis. Like, so omega is a 100 element vector, and then we're putting that into the 0 right here. So hz actually has a length of 100. So same thing with hp1, which is pole 1 has a length of 100, and pole 2 has a length of 100. So we want to divide those each point by point. So we want to divide the absolute value of the numerator by the absolute values multiplied by both of the poles of the first frequency, and then do that for every successive frequency. Therefore, our magnitude of our transfer function is really a function of omega. And so it's going to have 100 points because they're actually 100 omega points because we put in 100 frequencies. And then what we want to do then next is we want to figure out what the phase angle is going to be. So we found the magnitude, and we know from the math that we take the angle of the numerator and we subtract the angle of the first pole in the denominator, and then subtract the second pole in the denominator, and that gives us the angle. So this angle function right here in Matlab gives us the angle in radians. So a lot of times in engineering or electrical engineering, we think in terms of degrees. So we do that conversion here from radians to degrees by dividing by pi and multiplying 180. So now we're in degrees. So the next thing that we want to do is that recall that the negative sign right here, because this is really an inverting amplifier. If you remember, we erased the negative sign over here, but now we got to put it back in because we're looking at phase. So we subtract out the 180 degrees of phase shift that happens because this is an inverting amplifier right here. So that's what that does. It's subtle, but it's an important thing. So now we have the transfer function, broken into two parts, into the magnitude and phase of the second op-amp circuit. So what about the first op-amp circuit? So it has a gain of 15, and we computed that because we know the value of the R2 and the R1 in there. We abstracted that away earlier on in the circuit, and we got a gain of about 15. And the gain of the first stage only has a magnitude associated with it. The phase never changes. The phase is always 0 because there's nothing frequency dependent in it. So for any frequency, the gain is always just going to be multiplying by a constant. And we see that right here, where to make the transfer function of the whole system from the input over here to the output, we multiply the gain stage 1 transfer function by the magnitude of the bandpass filter or the second filter section. And then that gives us the transfer function magnitude. And because this doesn't have any phase sensitive components in it, the phase that gets computed for the bandpass filter is going to propagate through the system, and that's when it's going to appear on the output. So now we have a bunch of plotting. So I'm using something called subplots right here, so I can make a 2x2 tile plots. So I do things like I increase the line width and everything. So let's run this, see if it works. Okay, so here we have our graphs. So I'll make that full screen. So we have frequency is on the horizontal axis of each of these 4 graphs. So this first graph right here is showing us the transfer function of the circuit, and the trace with the blue dots in it is just the transfer function of stage 2. And we could see that if we look at the side over here, we have gain, magnitude, and volts over volts. So it's really V out divided by V in for this stage. And so what that's saying is that at the highest point, like at our most sensitive frequency, which is around 0.7, 0.8 hertz, we're getting a passband gain of 17.5. So that says that if we put in a 1 volt signal, it would multiply it by 17.5, and then we get 17.5 on the output. So we know that's not possible because we have a limitation on our op amps where they can only swing plus minus 2.5 volts from our 2.5 volt reference. So that's why we had that attenuator on the front. So the red trace right here is the magnitude of both stages. And so you'll notice that it literally just looks like it shifted up because that's the only thing the first stage is doing, because we multiply first stage times the second stage, is it's just multiplying by a constant, and we're seeing the effect of that right here. So we could figure out what that was. So we have 17.5, and then this is 272. And so if we do the division, I think it ended up being about 15. So we have a 15 for our stage 1 gain. So looking at the phase for both of those, they line up and they fall right on top of each other, because we know that the stage 1 doesn't affect the phase at all. Only the stage 2 affects the phase. So now we might want to look back at our transfer function over here that we made. So earlier on, we said that at very, very low frequencies, the numerator is really dominating the equation, because our denominator is just 1 times 1. And so we also know that the numerator always has a plus 90-degree phase shift. So it's saying very, very low frequencies, we're getting a plus 90-degree phase shift. And the phase shift from the two poles in the denominator is negligible, because if we calculate the angle here, so it's going to really be arctangent of the imaginary divided by the real, we'll find out we're right at 0 because we're along the real axis. So we have 90 degrees minus 0 is 90 degrees. So then why is this minus 90? It's minus 90 because we have to account for the negation from the inverting op amp. And if we negate something, that basically subtracts 180 degrees from it. So whereas we should have started out at 90 degrees if there was no negation right there, we're actually getting to minus 90 because we're really starting at 90, subtracting 180, getting to minus 90, and then we're starting to move along this path right here. And you'll notice as we get closer and closer to the pass band, so our phase is starting to drop more. So we're what we call accumulating phase delay, right? So more negative means more delay. And then at we call our best frequency, maybe our peak frequency of our bandpass filter, which is about 0.7 hertz, where we have minus 180 degrees of phase shift. So what happens at that point is the contributions of the phase shift for both of the poles are starting to weigh in more because we're starting to get more imaginary component because our frequency is increasing. So it just happens that we're starting at minus 90 and we're picking up another negative 90 degrees of phase shift. So meaning that the sum of both of these, we don't know which one is actually contributing more or less. Actually, we could figure it out, is 90. So we have our 90 minus 90, and then we're getting negative 180 because this circuit right here isn't really contributing to the phase delay anymore. So as we keep on going higher in frequency, you'll notice that eventually we asymptote at minus 270. And the reason that happens is because the frequency is so high. If we look back over at our real imaginary unit circle thing right here, that the arctangent of this is basically approaching 90 degrees. If J omega is very large, that means that the imaginary is very large compared to the real. So arctan of the imaginary divided by the real is going to be a very large number. It's approaching 90 degrees. So we have 90 degrees minus 90 degrees minus 90 degrees means that now the total phase contribution of this is minus 90 degrees. So if we subtract that minus 90 degrees from a minus 180 degrees that we got from our inverting stage, then we end up at minus 270 degrees. And it'll never actually get there, but it'll asymptote to it. So that is the analysis of the circuit. So the last thing I did was I added in the 1.3 volt function generator and then this poorly drawn voltage divider right here. And if you recall, we put the voltage divider in there so that we wouldn't saturate our op amps or cause them to clip. And now I'm driving the circuit right here with the 1.3 volt peak to peak source. And then I have that attenuator in there. So this right here, this output is a model of this circuit as we built it in the lab. So now we'll go back to the lab and see if it compares. Like in other words, when we're at 0.7 hertz, are we actually getting 3.54 volts? Say if we were at 0.1 degree, are we actually getting about minus 90 degrees of phase shift? And those are things we'll check with the oscilloscope. So let's see how our circuit winds up. We have our waveform over here. The function generator is set at 0.7 hertz. So that's going into our circuit through that attenuator that we were talking about. So we can go look at our waveforms over here and let's see what are we going to measure. So we'll hit the stop over there. So the amplitude of our input as determined by the scope is 1.28 volts, which is very close to the 1.3 volts that we're claiming is coming out of our function generator. And then the amplitude, so this is peak to peak amplitude right here. So the amplitude of our output, which is the blue waveform, so we're going from the peak to the peak right there, according to the oscilloscope, is 3.4 volts. So that's not too bad. That's pretty close to what the theory was showing us. So the theory from our Matlab was saying that the peak should be around 3.5 volts. So we're getting about 3.4 volts, as you can see from the readout down here, plus by inspection looking at the graph. Now, how about the phase? So we are expecting 180 degrees of phase shift at this best frequency, and you can see here that we are achieving that. Like the waveforms are basically mirrored across the x-axis right there. When this is high, that one's low. So that looks like 180 degrees of phase. So we could look at some other points, like say if we just take our function generator, turn our scope back on, and maybe we'll arbitrarily go down to 0.2 hertz. We don't want to go too low, otherwise we'll be here all day watching these graphs move. Go back to our oscilloscope. There, so we have a few waveforms. Let things run for a little while. Hit stop, and we can look at the magnitude first. So the magnitude of our input didn't change. It's still the 1.28 volts that we programmed into our function generator, but the amplitude of our output decreased quite a bit. So the scope is estimating it at 2.8 volts. So let's take a look. Does it make sense? At 0.2 hertz, what are we seeing on our magnitude plot over here? So you can go over here and find 0.2 hertz. It should be right around here. And it's showing 2.178. Not too bad. So our magnitude should be 2.178. Our scope was showing 2.8, so that's within the error of the components in the circuit. So how about the phase? So the phase is showing 127 or minus 127. And if we go back to look at the oscilloscope, it might not be visible there, but the oscilloscope is computing phase and it's computing it as minus 130 degrees. So pretty good alignment. So last thing we'll do is we'll turn the function generator up to a higher frequency. Maybe we'll go to arbitrarily 1.6 hertz. Get our scope running again. So we have our waveforms marching across the screen. So we're letting the oscilloscope acquire a full screen so that when it does its calculations, it'll have a good number. Hit stop, and our phase is 142 degrees. And then the amplitude on the input is still 1.28, approximately 1.3, and the amplitude on the output is now 2.84. Let's see, what do we get for 1.6 hertz? It's going to be around here somewhere. It's 1.4. 1.6. So for 1.6 hertz, it's showing 2.9. And if we go and look at our amplitude on our scope, it's showing 2.84. Not too bad. So 142 degrees of phase. Let's see, what is that going to mean? So if we go over here, and it's showing 208. So let's see, how do we interpret that? So we take 360 minus 142. So that would be 220. And let's see, I'm actually at 1.4. So let's see here if we get a few more points down. Okay, so now it's showing 213. So not too bad. Once again, things are lining up. So this is proof that you can model a circuit. So you could take a circuit that might be fairly complex with our EK307 knowledge, and then we can make a Matlab model, which we made as a script, and it's right here. And we made that model from inputs that we got from deriving the transfer function from the analysis on the board, and we could make a model that does a pretty good job predicting how our circuit will perform.